Hello and welcome to another episode of the OpelX podcast. This is a part of the Open Power Electronics project, or OpelX for short. Visit us online at opelex.net. That's opelex.net for past episodes, show notes, and more. This podcast is hosted by me, Lalit Patnaik. Currently, I am a power electronics engineer at AVL in Graz, Austria.
And I am Abhijit Kshirsagar, currently a faculty member at IIT Dharwad in northern Karnataka. Critical support behind the scenes comes from Sudarshan Kartik and Najat Abdul Aziz. In this podcast, we talk to leading experts in academia and industry in power electronics and allied fields. We hope you find this useful and entertaining. We are recording after a small pause in our schedule. But we are very happy to be back today with a very special guest, Dr. Kartik Iyer, who is a PhD holder from the University of Minnesota and currently works for Tesla in California. Welcome aboard, Dr. Kartik.
Thank you, Abhijit. Thanks for the kind introduction and having me on this podcast. As you mentioned, I got my PhD from University of Minnesota under the able guidance of Professor Ned Mohan, and then I joined Tesla in 2017. It's close to 5 years for me now, and I'm basically focusing on power converters and magnetics design that go into these power converters, and we basically put these in all of the Tesla vehicles, like the onboard chargers, superchargers, as well as any of the energy storage products. So I'm glad to be part of this podcast, and thank you for having me.
We also have with us Dr. Lalit Patnaik, who is now coming to us from Austria.
Yeah, I moved countries. I used to be in Switzerland, I think till the recording of our last episode, whenever it was. And now I moved to Austria to a new role. So I'm in AVL, a company called AVL, which provides automotive testing solutions, at least in the department that I work in. Yeah. And hello, Kartik. Glad to have you on board for this interview today.
Yeah, nice to meet you, Lalit.
Kartik, so I'm going to cut to the chase. Tesla is a dream company for a lot of engineers. Can you just describe briefly your engineering education journey that led you to this position?
Yeah, no, absolutely. I'll be glad to share my pathway or my learnings through that and how I eventually landed up at Tesla. So I think way back, basically, I jumped into engineering after my 12th boards, and then I had the option of getting into an NIT. That's how I landed up with electrical engineering to begin with, and basically in it, we all of us are mostly aware of the course curriculum that we follow in India, which is heavily focused on learning different subjects and less of the practical stuff, at least in the beginning of the undergrad. But during my third year, I had the good opportunity to work on a hardware project, which is basically a solar PV panel, trying to charge a battery, and I kind of made a really small voltage regulator circuit. Got the experience of simulations, doing some hardware experiments, and that basically led me to love this particular field of power electronics, because I felt you do a lot of simulation work. At the same time, you also do hardware work, or do experimental prototypes, see the actual thing like a battery charging and all of that. So that definitely gave me the merit to continue pursuing this field. And after my fourth year, I kind of ventured into applying for a master's degree and I was able to get an admit at University of Minnesota under Professor Ned Mohan. So that's also in a way a dream experience, I would say, because everyone in India has read his books, not only in India and worldwide. Right. And then it's really a great opportunity to be able to have work under him. So that was basically my transition to like masters and then PhD, and that kind of paved my way to like getting an internship at Tesla towards the end of my PhD, and then through the internship I was able to like jump into a full-time opportunity.
Yeah, that's very nice to hear that you took that let's say plunge into industry right after your PhD, because a lot of people, like for example even myself, we let's say take our time to decide whether or not industry is right for us or not, and then I spent a few years in postdoc, and yeah, that was also nice, and it's also nice to see that there are people who directly do that transition, and it's becoming, I would say, more and more common these days.
After you finished your 12th, did you ever have this certainty that yes, I want to do electrical engineering in my BTech only, or were you open to other branches, or was it sort of chance that you took up electrical? How can you share something about that?
Yeah, there were different domains. I did not want to get into computer science more because I didn't connect so well with like coding and algos and all of that to begin with. And then electronics definitely at that time seemed more fancy. The electrical was definitely like a core branch, and in my head it was more like I either get into electrical, mechanical or civil, which are like the core branches, and it so naturally happened that I preferred electrical over mechanical. NIT Surat, by the way, is known for mechanical engineering more than electrical engineering, so it was very like non-obvious for people to digest the fact that I chose electrical engineering with the kind of rank that I had, but I still went ahead with electrical, and I don't regret that even a bit. I think along with electrical, the choice of moving into power electronics at that time, because it was also a very niche field, right? Like in India, it's more of machine design and control systems and whatnot, and power electronics wasn't something like a booming thing. It's just that, over the last 10-15 years with the landscape has just changed, and power electronics becomes like a really great field to be in. But I think I just followed the interest that I had, learning different courses and being exposed to different fields, and just naturally got into the PE domain.
Kartik, can you name maybe one or two teachers whose courses or interaction with them was really impactful in your educational journey?
Yeah, I would say like I had taken some power electronics courses during my undergrad. Like there was Professor M.A. Mullah and Professor R. Chudamani. I think those were the two professors who used to teach us power electronics, and I was really like more focused during those classes and as compared to the other subjects, and that's where I kind of knew that this is where I'm more interested compared to other things. I think that was basically like a couple of courses and then I used to come back and read Professor Mohan's books and then kind of learn the thyristors, and that's what we basically learn and understand, and I kind of paved my way that to be my final year project as well, to do like the HVDC light and whatnot. That were the fancy terms back then by ABB. So that was basically like I knew like this is where my interest lies.
Nice. Okay.
So now that you are in Tesla, I would like to know what your average day looks like the day-to-day work that you do and the kind of tasks that keep you busy.
I think that's a really good question. The way I would think about it is basically Tesla being a relatively large organization, that there are too many things happening. So you basically get involved in like a few different projects is how I think about it. They would all be around your domain, but then it would be in a way that in some of the projects it's you require like a cross-collaborative approach, like you would have many cross-functional teams and you need to align on specific goals with them and make sure that the goals are clearly communicated and you work towards it. On a individual perspective, what that helps is it helps you to grow your breadth in the particular field. Like we all are, power electronics is our core domain, but then working on some of these projects, you really improve your or increase your breadth. I would say that is, you would learn more from the mechanical aspects of a certain design, the manufacturing aspect, the reliability aspect, and all those things. And then the next set of projects is usually like it's core technical, where you are trying to improve your existing design, or actually are trying to design something unique or new for the specifications that you have. And that's really like your core domain, where is very similar to the PhD work that you would be pursuing. So it's like a mix of both worlds.
So, Kartik, transitioning from academia to industry, is there something that you had to learn afresh or different transitioning into industry in terms of not just technical skills, but work skills or work ethic? I'm not sure how to define it, but is there something that you had to learn as being part of such a team in industry?
Yeah, I think that's also like something that's very non-obvious, right? Like when you are in an academic world and more of as a PhD student, you kind of know what's your PhD project and you are at it and you keep working at it. It's very similar to the second type of work that I describe at Tesla, where it's like your technical expertise and you work towards it. So in that, I would say one difference is you are able to understand, okay, in PhD, you may be working on a very niche or trying to prove a very unique converter concept. But then say at Tesla, what it teaches me is that, okay, we want to make this for millions and millions of cars or hundreds of 10,000s of energy storage products. So how do you like design this, which is like easily manufacturable or like can work for the entire range of tolerance for the particular component? Like in PhD, I would not demean it, but then it basically will allow us to like prove it at a certain operating points and we are good. But because this is like a product, you have to make sure that it works for all the different corner cases and things like that. So that's a technical challenge, I would call, wherein basically you run the risk of trying to validate each and every case and also try to compete with the existing designs. If you have like a new novel design, you need to really prove it's cheaper, it's manufacturable, it solves all the constraints, and then only it can qualify itself to be a product. And I think for the second part, on the soft skills side, it's basically like working as a team player or a team member. Like you need to make sure you are just not going ahead or have a clarity on what the end goal is, but you are able to equally communicate with everyone else in the team as to what that end goal is, and they can also march towards it.
So Kartik, when it comes to power electronics and power in general, sort of the proof sort of is always in the hardware, right? And in academia, we do research in a certain way. I mean, we try to build, we do a little bit of simulation, we do analysis, and then we build the hardware, then show it works, and then that's sort of the end of it, right? Is there a difference in how the balance between simulation, prototyping, and then proof of concept development, is there a difference in how that balance is approached in industry, and do you think there's some change needed in how we approach it in academia, whether at PhD level or at masters or lower levels?
Basically, if I have to tell it from my experience during my PhD, mainly like you have to like finish something in a good 5-year or a 6-year timeline, and by the time you understand or you start reading papers and understanding papers and finishing your coursework, I would say it usually takes like a good 2 years. At least that's what happened in my case. And then by the time I start reading papers or arriving at a problem, doing simulations and showing something is new and pushing that envelope a little, it's like 2 more years. And then by the time I build my hardware and I have everything ready, it's almost time that I need to graduate and move on. So it's really like we are rushing towards getting the results in the hardware and things like that. But and that's where in an industry where I think is like you basically start with that hardware and then you build on it and you learn from it. But I think I also see that trend changing in some of the universities here in United States, where basically like there is a new set of PhD students who inherit the hardware which is done by the previous set of students, and then the professors and the postdocs are like the link in between where they continue to drive that research ahead. And then it's more of not only like concepts and new converters or new modulation, but they are able to answer like the real world layout challenges, be it the control challenges, be it like transient capability and whatnot, like the things that also make the research work like a product based concept. I do see that some of the universities are indeed picking that up and not only stopping with like one hardware and one concept, but taking it ahead. So I think that change is definitely happening, but that's what is trying to close the loop between, or close the gap, I would say, between the industry and academia.
Would there be some examples of, I don't know, memorable burns or some experiences where you had a setup that burnt some components or that taught some interesting lessons? Because this is a common theme to almost all power engineers. I mean, also in the lower power or even analog electronics world, people talk about magic smoke, but I guess in the world of power electronics there are magic explosions rather. So would you want to talk about any of those?
Yeah, absolutely. I think I wouldn't say we all, but definitely I went through that experience, and it's not the best of the experiences. So basically like you end up building a hardware for yourself, and then it's a good 3 months, 4 months of just soldering all the boards and having
or more rather, in some cases.
Yeah, definitely, like easily 4 to 6 months of soldering all the units, the boards, and then assembling them together to build the hardware. And I think in the initial 15 days or a month or so, I was extremely careful about the hardware that I'm building to be like making sure I do each step correctly. But once you get it to a certain stage, and then if you are slightly reckless, then the hardware tells you that you cannot be. And then you realize the amount of pain that it takes to like fix that thing, identify it, fix it, and again bring it to a stage where it was. And basically that is one mantra that kind of I learned, is that I don't think personally I would ever use the hardware to teach me what I want to learn. It's basically only a way of validating what I already know, either through simulations or analyzing the circuit. Like when I try to turn on the hardware, I personally try to make sure I know what kind of a waveform I'm expecting, and not the other way around. Let the hardware tell me what waveform I'll get, but it may lead to some consequences that I don't wish to have.
Yeah, definitely. So. And the other point is always having a co-worker who is prepared with the, like, standing close to the red button to close down power if something bad happens.
Exactly, the emergency stop that we always want to have.
So, Kartik, just taking off on that point about simulation, what is your feeling about the role of multi-domain simulation? So already, there are some packages that do electrical plus thermal, but if you want to take it a little bit further, you want to do electrical, magnetic, thermal, and maybe, things like cooling and all. Do you think there's a place for such detailed simulation at the student level, whether even at the PhD or postdoctoral level, or do you think it's best left to companies only?
I think there is always ways to have it both at the industry level as well as the student level. One way I think of that being feasible in an academic setting, Abhijit, is like maybe when we write these proposals and grants and things like that, then we can have like electrical professor in power electronics and say someone from the mechanical thermals who write a co-proposal and has like a one dedicated PhD student who is enabling the thermals work, and then it can be like a cross collaboration where we have an expert on the mechanical side solving the thermals or solving any of the magnetics issues can also be a way to think about it. But it can be like a proposal which has cross collaborators from like different domains, and we have the tools. It's just that it's very difficult to expect a power electronics PhD student to have the same level of thermal impact as well. Then it can be like a cross collaboration thing. If that's feasible, that will be ideal.
Yeah, I just thought I should mention here, because we are talking about thermals. I just started reading an interesting book, so I thought it makes sense to mention it here. This book has an interesting title. It's called Hot Air Rises and Heat Sinks. It's by Tony Codiban. I think he's a mechanical or thermal expert. So yeah, I think I got into it because, as you rightly pointed out, thermal management is more and more important for power engineers, probably even more so than other electronics and engineering fields, some of the other. Yeah. So I'm happy that you brought out this important aspect as well.
So, Kartik, coming back to multi-domain and something that is very much your area of expertise, let's talk a little bit about magnetics. Can you tell me a little bit about how you learnt magnetics from the undergrad level all the way to, your present level of expertise?
I don't know how I learned magnetics, right? That's because it's hardly anywhere present. But we are currently seeing like it definitely has a significant impact, and I'm seeing more and more industries kind of open these job portals and responsibilities. And I really feel like we were talking about thermals, but along with thermals, the magnetics is basically an electrical component, and we can't imagine like a power converter except you go for like capacitive, wireless and things like that. You always either have an inductor or you will have a transformer in your circuit one way or the other. So definitely like the magnetics thing is very important. And for as far as my experience or my journey is concerned, it kind of so evolved that I got pulled into the magnetics work during my master's time at University of Minnesota. We had one of our PhD guides who was my mentor, and he kind of introduced me to magnetics, and I just started doing ANSYS simulations slowly, and then kind of started reading into papers. There was hardly any university who was doing like proper magnetics work at that time. But it so happened like because it was such a niche area, there were like hardly people, and then I got an internship at Cummins thanks to my magnetics work as well, and there I was able to develop more of my knowledge, and then I got an internship at Tesla, so it kind of automatically happened that I got pulled in. There was only one course or like one of the few sections in Professor Robbins' Advanced Power Electronics course on magnetics, but other than that, it's all due by reading papers and picking up in the lab, and that's where I feel like it will be extremely helpful if we can all sit together and have like a proper course or a curriculum.
So, Kartik, very controversial question, and I'll request you to answer honestly. Do you think that this reluctance equation that is usually taught in undergraduate, you remember what I'm talking about?
Mm-hmm. Yep.
Phi is proportional to MMF.
Yeah.
Do you think it's time we do away with that and not teach that at all?
I will say we don't teach that at all. We need to start somewhere with the basics, but then we also need to add those exceptions, saying like maybe it may not hold under this scenario, or maybe it needs to be slightly modified under this scenario and things like that. I think it's basically we need to definitely start somewhere, but kind of evolve in a way to like, I think at that time there was hardly any simulation stuff, but now you have these simulations where you can observe or see the B field, the current density, and understand that, right? Like previously it was very difficult to communicate like, okay, well, how is the B field, how is the current density, but now all the high frequency effects, everything like that can be explained through simulations. So that's where, and if visual pictures, I feel, is like a great way to communicate what the learnings actually are. So that may be one of the ways that we can.
And just I had, because you are talking about magnetics, and Kartik, you have a lot of experience with magnetics design as well as designing magnetics for large scale production. I think the question that is becoming more and more important now in magnetics is, how do we make traditionally, let's say, conservative field that is really old, magnetics design is centuries old, how do we make this field catch up to these new devices, wide band gap devices like silicon carbide, gallium nitride with this large DVDT, DIDT? Do you have some thoughts about what we could do in the magnetics design field so that they don't lag behind and they are able to use these large wide band gap devices in power converters?
Yeah, thanks, Lalit. I don't know if I should open up more controversies, as like these things are all over LinkedIn and all of that. I have been like gone through so many like interactions and just different opinions and different thoughts. I think personally, I would feel like everything starts with just educating more people, and more people have doing it and finding it, right? Like I remember when I was graduating as a PhD student, modular multi-level converters just began, and now like in 4 or 5 years, the number of people who are working on modular multi-level converters is just like revolutionized the entire high voltage, high power converter domain, and there's just so many learnings from so many people. So I definitely feel like the place where it should start is we kind of create that interest and we kind of teach students the importance of it and have like more funding opportunities to explain the real world consequence. And then we will definitely see like we move ahead leaps and bounds, and it can come from any direction, right? It can come from better magnetic core structures, better designs, or it can come from like better converter topologies, because engineers will start understanding magnetics, so they can come up with converter topologies that improve magnetics. Now it's more like they would design the optimal converter and we would just put in a magnetics which works for that converter. But tomorrow maybe we can think of topologies if people understand magnetics more than what they might. I'm not saying people don't, but then if there's like a way that they can learn even more, then maybe it can be like the converter topologies aid in designing help the magnetics, and that way we can get a balance or shrink the gap that we currently see. I think definitely I feel like the only way is more people getting into it, more people solving those problems, and we will definitely find better solutions.
Kartik, it's interesting that you mentioned optimizing or changing the design of the converter to match the magnetics. Could you give a small example to illustrate how this might happen?
One way to think about it is usually it's dependent on the energy storage. Like the inductor is basically energy storage and the transformer is the total power, VI and all of that. So if there are like ways where we think about reducing the energy storage in that inductor, or otherwise like think about topologies which try to reduce the energy storage more and more, and also like think about ways of modifying it or changing the converter in any different way to just reduce the total power that the magnetics have to push through or consume. Then that can be ways where, I'm not saying it's not putting the burden on anyone else. You go improve your converter, we won't improve the magnetics design, but it's more like one way to solve that thing. But the thought process is like if more people are involved in magnetics design, maybe we can inherently improve the magnetics designs.
I guess one of the key points here is that when it comes to many of the semiconductor devices or even passive components other than magnetics, we use a more off-the-shelf approach as electronics engineers, where we can just use what is available in the market as a component, whereas with magnetics is almost always some amount of custom design of the component, which let's say doesn't happen when you want to use a capacitor or an capacitor or a switch or something like that. So because of this need for very custom designs, there is need for a lot more interaction or co-design between the magnetics experts and the power electronics expert, which does happen, but maybe it needs to happen earlier in the design stage of products.
Yeah, no, I would fully agree with that. I think the best way would be like either person understands the other domain, and as well as like is not maybe this has the same level of expertise but a really good understanding. And I'm seeing that trend now changing, like in the past few years since I've been employed at Tesla. I really see like a lot of universities and a lot of professors have started, who have been traditionally designing converter topologies and stuff like that, have started venturing into the world of magnetics and have started taking it. So the students who graduate under them kind of have like the knowledge in both the converter design and the magnetics. So I would definitely see that trend changing, but I would hope that it changes and is adapted a lot more to help.
And I thought I will also take this magnetics discussion as an opportunity to take or mention one of the quotes that I take from Robert Memano. He was founder of Unitrode Semiconductor Corporation, which later became part of Texas Instruments. Retired as a Texas Instruments fellow. He was the creator of the first switching power supply controller, the SG1524. So he had written in one of his books, the design of magnetic components is the easiest place to jeopardize a power supply design project. So that's how important this one component can be in the whole power supply. If this is not done well, it doesn't matter how good the topology is and the control is, you will just have a lossy power converter. I thought it's worth mentioning this. And also, since we talked about resources in magnetics design being hard to find, I thought I'll just mention this one website. It's called Encyclopedia Magnetica.
Interesting.
You can just search it online, e-magnetica.pl. It's by a Polish professor. I don't quite remember the name, I'm sorry, but you will find it on the website, Encyclopedia Magnetica. So, okay, one more resource that
absolutely
on magnetics that is hard to find.
Definitely.
Awesome. Kartik, moving on to a slightly more broad view, what do you think over the next 20 years, what are the main challenges or problems that will come up in power electronics design that people will be trying to solve?
Yeah, I think that's looking into the future, right? Like we keep on expanding with silicon carbides are more like a norm at the moment, and I think that I see a lot of emphasis on gallium nitrides and things like that. So I think those are definitely places where
wide band gap.
Yeah, wide band gap is definitely commercializing it, like all of the various aspects, pulling it into production, cost and all of that would be where I can see like potentially things changing or improving over the next like 10-15 years and whatnot. But at the same time, like since if we continue expanding more and more into using power electronics as part of our daily lives, say through EVs or say through all this energy storage products and whatnot, then definitely feel like with the more improvements in all of these technologies, we should see the power density and those guys depleting significantly. And one way would be to either improve our passive technologies like capacitors, magnetics and EMC filters and all of those things. So definitely more of topology research. I don't see that stopping anywhere, but that would be like...
Do you also see more and more nanocrystalline core materials and maybe some other insulation materials, all of this materials research coming in more and more to aid the magnetic components with dealing with these wide band gap devices?
Yeah, no, I think that's a great point, Lalit. I did not mention that, but thanks for bringing that up. I think that's definitely an area where I think there has already been some research that has begun. Like I see a couple of universities having like a collaboration more with the materials team. As I mentioned, like mechanical thermals is one aspect, materials can be the other aspect, where you can actually co-develop a material and then try to see or make a material for your own specific needs. And potentially I see that research happening on the magnetic side, but we can also envision on the device side, like maybe for a specific application, you have like a device which is custom made for that particular operating points and that particular scenarios and topology or application. And that's definitely a place where things can improve multiple forces. Like materials I see is the base, right? Like if you change a material, then your performance just goes like 10x. So as long as materials is definitely the fundamental. So I would fully agree, like more on the research academia side, if there can be like novel materials for maybe specific application or a generic application, they just open doors for sustained innovation.
Just to follow up on Lalit's question, do you see any specific new materials in the magnetics space that we should be expecting to cause some revolutionary changes in the next maybe decade?
Currently, no, but I'm sure like there should be something happening in the near future. But unfortunately, I don't see anything happening at the moment.
Okay, yeah. Let's switch gears a bit to a slightly different topic here, and this is with regard to recruitment. So when we want to solve problems in engineering, the moment the problems are slightly complicated, we need more and more people, and so we need to build teams. And so what is your strategy, or what kind of challenges do you face in recruiting students from research programs, or I don't know, even younger engineers into your research and development teams, say for example at Tesla?
Yeah, no, that's a good question, Lalit. I think basically, like as I mentioned previously, there are like different aspects of the design where as a PhD student you would have that technical depth, but it is very hard to find that breadth into different fields or like cross-functional domains and all of that. So that definitely is something that we do see the fresh graduates kind of lacking in a way, right? They have a really good technical expertise in the power electronics domain or maybe the magnetics domain, but they would severely lack like the cross-functional domain experience. But as we speak about it, like maybe having a thermals curriculum in the graduate programs or having the magnetics curriculum in the graduate program can kind of help bridge this gap. And as well as like if we have like strong internship programs for the graduate students and they kind of get that industrial experience, it's up to the students to choose the industrial route versus the academic route. As you mentioned, like currently more PhD students you see trying to prefer the industrial route as well. So it could be like maybe the internship programs are more streamlined. And as being in a company like Tesla for like a few years now, I definitely feel internship is not only essential for the students, it's also essential for the people inside the company, because it's very hard to find out through interviews like how good a candidate is. Maybe someone can do really well in an interview, but actually while working you can really see some shortcomings, whereas the other side, maybe the candidate is not able to do so well in the interviews but is a really strong candidate overall. So I think definitely like those internship programs can help bridge the gap between for the students as well as for people in the industry to have a flavor of what this particular person can bring on the table, and not only the technical skills but the soft skills and things like that. So that's a great question. I think I would say something we lack, but a more organized way of the internship programs, and can definitely help to bridge that gap.
So if I may ask, related to that question, but sort of the flip side of it, for a student who's, let's say, just entering their bachelor's program right now and is interested in power and is, wants to get into the power electronics, power engineering field, what are some of the things that they should be focusing on or trying to inculcate in their studies right now, so that they are a good resource person or they are a good skilled engineer when they finish their bachelor's, or if they go on for masters when they finish their masters?
I think that's a really good question, Abhijit. One thing that comes to my mind is I've seen at University of Minnesota and as well as a lot of universities in the US which have like these SAE events or like electric vehicle competitions where it's focused for undergrad folks, and then they kind of build their own electric vehicles. They kind of run through competitions, and that's a great place where you get a flavor of like hardware engineering stuff, because we really don't want people to be focused on simulations or analytical equations as we talked about. They should really get that hardware experience, and once you have that, you kind of know, okay, you want to build things and you learn from your mistakes, and that kind of nurtures a very good thing in their domain or the profile, and which can be really helpful even if you graduate as an undergrad. It kind of gives you, do you want to learn more, you go back to school and get into a graduate program, or you feel you have had enough and you want to build real things, then you start getting into an industry. And the kind of experience you have also helps in the industry because you have solved hardware problems or you have built things. So that's definitely something that I would encourage for more schools to adapt or find ways. It need not be electric vehicles per se, that's just an example, but different ways that people can venture into like getting that hardware knowledge or skill set.
Maybe even students should be getting credit for these kinds of side projects that students often do for these competitions, design competitions, robotics competitions, Formula Electric. This is kind of a stream where students are doing this on their side time. They have their courses running, they have their labs running, and they do this on the side. But because they gain a lot out of this practical experience and building hardware experience, maybe if we give them some credits for these kinds of projects, it would also push them to explore more of these. So that's a very good point, Kartik.
Yeah, no,
so I don't know, just to mention what we are doing. As an undergrad, I don't think there was much in the way of, getting credits for these kind of projects. Of course, we did a lot of small robotics projects and things like that. But now, especially with the new education policy, right, NEP, there is some specific weightage given to extracurricular projects like this. And then IIT already has a system where we have two kinds of projects. One is called Additional Learning Opportunity, ALO. And the other is, we've also introduced what is called an R&D project. So they basically join a lab where, there are PhD and MS students working on research problems, and they can solve a part of that problem, work under that advisor, and that's called an R&D project. So other than BTech project, they have the opportunity to do, R&D effort right at the beginning at the undergraduate level. So I think what Kartik is saying is pretty much similar to what this could be as well.
Yeah, no, absolutely. I believe that will be really good. The faster you get your hands on hardware, I think definitely the faster you kind of start learning, right? Like you can keep doing simulations or calculating analytically unless you like get the real hardware. I think the learning is like completely different.
Yeah, it's the only way to close the loop of learning. I mean,
Exactly.
Simulation and analysis is open loop in a way. It doesn't give you feedback.
Lalit, anything else? I think we have covered pretty much all the talking points that we had sort of planned.
Just one more thing. Kartik, do you have a message, like in one or two lines, a short message for all the younger engineers who are getting into this power field or who are not yet into the power field and are thinking about, should I go into this or should I go into something more flashy? What's your message for young engineers who are dabbling about power electronics?
Yeah, I think the only message I would have is that computer science and all of these other domains are like extremely fascinating, and AI and machine learning are like the key things floating around, right? But I really feel like kind of the real engineering or really building something real learning comes from actually building something, seeing something in front of you, and then getting your hands dirty in a way. And I think that's where I really like the power electronics domain, because you can do analytical stuff, as we talked about those reluctance equations. We can do like simulations, FEA and MATLAB and all of that, and then we like get the real hardware where we try to visually see things like, say, a battery charging or like electric vehicle or moving and things like that. So I think if you want to merge the real physics that's happening, I would definitely that's a way for people to like, if they cherish that, then this is a really good place that they can begin with. Like, and then there are always ways that we can include AI and machine learning, all the fascinating things into like, say, the converter modulation or like, device operation and magnetics design and whatnot. So there can always be paths and channels to have that. So it's never away.
Okay, so thanks again, Kartik, for taking the time to talk to us and sharing a lot of your interesting insights. Once again, thank you for being a part of this OpelX podcast, and hope to be in touch with you soon again. Thank you.
Thank you very much. Thanks, Abhijit. Thanks, Lalit, for having me. And yeah, I'm really glad I was able to like have a very open interaction and also kind of vouch for more interest and more things that can happen on the magnetic side of things for the power electronics community in general. So I really appreciate the support and the platform for able to share my thoughts and opinions. And yeah, thanks again.
Kartik, where can our listeners find you online? Are you on social media or any other platforms?
I am on LinkedIn, so LinkedIn is definitely a platform where I actively use and am available. So yeah, it's always there on LinkedIn.
Okay, so we'll add a link to your profile on our show notes page.
Yep.
Okay, thanks again, and